Have those notebooks out and open. This is for Mr. Markey's Algebra 2 students. It is time to review factoring. Factoring is going to play a major role moving forward into the lessons for next week, and I need to make sure that you're on top of this. So, let's begin. There were several main things that we did within the realms of factoring. When it came to quadratics, we mainly focused on the Tucker method, and I'm going to review the Tucker method with you shortly. For higher level polynomials, we did synthetic division, in which, again, I will review that with you shortly. There are some other forms that I can do with you that you may not have seen before. That's up to you whether or not you want to use them. I'm going to show you various comparisons that you can do. Let's start with something very basic, very simple. Let's just deal with a quadratic. Now, remember, when you are dealing with quadratics, you are dealing with an equation in the form ax squared plus bx plus c. Three terms. Sometimes you might have two, sometimes you might have one, but that's a whole other situation. Typically you have three. Let's start with this basic example. Now I'm going to suggest to you that as you go throughout this video, pause every now and then and attempt the problem on your own first. Then see whether or not you got it right. And if you did or you didn't, well, we can talk about future problems and what you could potentially do in order to help yourself get these things done correctly. So with the Tucker method, which I will write off to the side in a moment, there were 5 main steps. Now, with the Tucker method, some of these steps can be skipped at various points. In fact, the first step of this particular problem we can actually skip, and I'll talk about why in a moment. Reminder, the Tucker method is mainly for quadratics. There are some cases that I will show you, actually today. There are some cases that you can use the Tucker method on that they're not quadratics, but those are few and far between. Step 1 is always the same. Step 1 is to take out a greatest common factor. You look at all 3 terms, you try to determine whether or not they have anything in common, whether it be a variable or a coefficient. Now, in this particular instance, you have a 1x squared. 1, 7, 18. The only thing they have in common is 1. You can't do anything. You move on to step 2. If you have a GCF that is not 1, you have to make sure that you double check to see if you can take anything out. Sometimes you can, sometimes you can't. Especially if that a term is a negative 1. You better believe you got to take out that negative 1. We need our a value to be positive. But since we can't do anything, we move on to step 2. Step 2 is to just simply multiply a times c. Now, a times c in this case, we do have a 1 and 18, but you got to realize that that is a negative 18. A times c will give us negative 18. Always make sure you are multiplying by the a. If that a is not a 1, you got to make sure you're doing it correctly. Step 3 is probably the most important step in this entire process. Step 3 is to find your 2 magic numbers. Now, your 2 magic numbers have to do 2 specific things at the same time. They have to multiply to whatever you got for a times c, and they have to add to whatever the b value is. Now, in this case, again, I'm trying to find 2 numbers that multiply to negative 18. I could list out a bunch of different pairs involving 1s and 18s and 2s and 9s and 3s and 6s. Or you just take a moment and think to yourself logically, okay, I need 2 numbers that multiply to negative 18, and they have to add up to negative 7. If you take a moment to think, if you try to list out some pairs, by all means do that. Ultimately, the numbers that you need are 2 and negative 9. It does not matter whether you write them 2 and negative 9 or negative 9 and 2, but the 9 has to be negative, because those 2 numbers have to add up to the negative 7. Now, being they are magic numbers, we could move on to step 4. Now, step 4, for this particular problem, we don't need to do, but I'm still going to show you so you have that understanding. Step 4 is t-chart / simplify. Now, it's not going to happen on this problem. We're not going to simplify on this problem because we don't have to. I will show you in a couple problems something that actually does simplify. Our two magic numbers go in the bottom. In the top of the t-chart, well, you look at this first term, this ax squared. It's a 1x squared. In this case, we're going to do a 1x and a 1x. Factoring is the process of breaking these things down. If it were a 2x squared, we would do a 2x and a 2x. But again, future problem. The reason why I say we don't have to simplify here is because, well, you vertically, you look at these two numbers and you think of them as a fraction. The fraction 1 over 2. Can the fraction 1 over 2 simplify? It can't. The fraction 1 over 9. Now, yes, there's a negative. Leave the negative where it is. That's important. But look at the fraction 1 over 9. Can't simplify. Since you can't simplify, well, we'll just simply move on to step 5. Step 5 is to write the factors. Now, again, notice I did not say answers. I said factors. The factors vertically here, it's a 1x, 2, 1x plus 2, or just simply put an x plus 2. Vertically, this is a 1x and a negative 9, or just x minus 9. These are our factors. Now again, it depends on what the problem is asking. If the problem is just simply asking for you to factor, then boom, we got it. If the problem is asking for you to solve, then you have to go a little bit farther. And we'll deal with that maybe in another video. But today is just about reviewing factoring polynomials. Let's do another quadratic. I'll do another basic one, and then I'll do one that's a bit more complicated, to say the least. Let's try this one. Let's try m squared minus 9m plus 8. Now, again, pause the video now if you want to give this one a shot on your own. Otherwise, follow along. It's a 1m squared, so do not have to worry about, a GCF in this case, because the GCF is going to be 1. Well, unless each term had a variable in it. If each term had a variable in it, then I would have to deal with something. It's almost like I'm foreshadowing something for a little bit later on. Anyway, since the GCF is 1 and I can't take anything out, I'm going to move ahead with a times c. 1 times 8 would just simply give me 8. Now it's time for my magic numbers. But I need you to pay attention to something here. The magic numbers have to multiply to a positive 8, and they have to add up to a negative 9. Multiplying to a positive, adding up to a negative. At this point, you should realize, oh crap, both those numbers are negative. The magic numbers, that is. So, two numbers that multiply to negative 8 would be like, what, negative 2 and negative 4? No, those add up to negative 6. Oh, but then you realize that you could multiply negative 1 and negative 8. And they add up to negative 9. So, I go about my t-chart. Now again, for this particular problem, because it was a 1m squared, technically I don't have to do a t-chart. I don't have to do the step 4. But I'm going to do it just so you can see it. Be a negative 1 and a negative 8. My magic numbers go in the bottom. And then in the top, it'd be a 1m and a 1m. Now again, nothing can simplify. Again, the negative has to stay on the bottom. 1 over 1, nothing. 1 over 8, nothing. Again, the next problem, we'll see what happens. This would be an m minus 1, because vertically right here, this is a 1m minus 1. Same thing here, 1m minus 8. These are our factors. You can check to make sure that you did this correctly by multiplying these two back together. You could do a 2 by 2 box. You could do distribution. You could do FOIL. Whatever the heck you want to do. I'm not a fan of FOIL. It hurts my teeth. I'll show you on a future problem how we can actually multiply them to show, oh, I did do this correctly. But let's try something else. Let's try a problem where something does need to simplify in that t-chart. Let's try this. Let's try 2b squared plus 17b plus 21. Step 1, always check for GCF. 2, 17, and 21. The only thing they have in common is a 1. So, I can't do anything. Move on to step 2. Step 2. A times C. That'll get me 42. 2 times 21 is 42. I need to find two magic numbers that multiply to 42, and at the exact same moment, they have to add up to 17. Oh. Okay, 42. Well, 2 and 21, but 2 and 21 add up to 23. 6 and 7, but 6 and 7 add up to 13. With your calculator, perhaps you can do something like this. You got 42. Clearly dividing it by 2 doesn't work. Bring it back, divide it by another prime number. Oh, there it is. Whoa! I didn't think it would happen that soon. Or did I? 3 and 14 are my magic numbers. They multiply to 42, and at the exact same moment, they add up to 17. Now here, I have to do my t-chart. I have to do my t-chart here. My magic numbers go in the bottom. In the top of that t-chart, since I have a 2b squared here, I'm going to break it up temporarily as 2b and 2b. I'm not going to make the joke. I'm not good. Anyway, it's t-chart / simplify. This is a 2 over 3. That doesn't simplify. Screw that. This is a 2 over 14. That does simplify. Since it does simplify, you need to reduce that fraction. Keep the b on top, but you reduce that fraction. 2 over 14 reduces to a 1 over 7. I'm done simplifying. Now, sometimes you can simplify with one of them. Sometimes you can simplify with both of them. It depends. It depends on the problem. Vertically, in the first column, I have a 2b and a 3. My factor is 2b plus 3. In the second column, my simplified column, I have a 1b and a 7. I have a b plus 7. Now, I am going to multiply these two back together just to show you that they do indeed give me the original quadratic. But this is my answer, the factors of this particular problem. Let's set up a check, checking our work. Now, again, you don't necessarily have to do it this way. If you wanted to, you could use FOIL. Stay still. You could use FOIL. You could use distribution. You can do whatever the heck you want. I do box. There's a 2b and a positive 3. There's a b and a positive 7. Now, this is just checking my answer. First box, multiply 2b squared, 3b, 14b, 21. Multiplying out that box. Combine like terms, 2b squared plus 17b plus 21, which is exactly what I started with. That just confirms that I did the problem correctly. So, let's try another one. Now again, I'm going to stick with quadratics for a little bit, and then I'm going to show you some more complicated examples. We'll see how that goes. So let's see. Again, I encourage you, if you're watching along and you're trying on your own, pause the video once I write the problem down. Pause the video once I write the problem down and give it a try on your own. We got another quadratic here. Mr. Markey, I think you forgot the last number. No, I didn't. I did not. It's still there. What is that number? The number that's missing is the C value. The C value is missing. Oh, is it? It's technically a plus 0. You could put that 0 in if you wanted to. I'm not. I'm going to leave it be. Instead, I'm going to continue with the Tucker method, exactly as I have it. Step 1, GCF, greatest common factor. Mr. Markey, 7 and 9, they don't have anything in common. But both terms have a variable in common. The constant's not there. They both have a k in common. So, I can factor out a k as a greatest common factor. A greatest common factor does not always have to be a number. It could be a number, it could be a variable, it could be a number and a variable. It depends on the situation. If you divide a k out of the first term, you end up with 7k. And if you divide a k out of the second term, you just get a 9. Okay, Mr. Markey, let's continue with a times c. What a times c? See, you're done, technically. The second that you factored out that variable, and this only really works with variables, but the second that you factored out that variable, this stopped being, what's inside the parentheses, stopped being a quadratic, and it became linear. The whole purpose of the Tucker method is to factor quadratics. This is factored. When you end up with these two terms being multiplied together, that's being factored. It works. Let's try another one with a GCF. Really weird. Do I want to do that one? I think I do. 28 n to the 4th. Oh, Mr. Markey, what are you doing to us? Plus 16 n cubed. I'm going to turn off this video now. Why am I even bothering with this? Minus 80 n squared. I love this problem. This is a quartic, for the lack of a better term, a 4th degree polynomial. But we can still use the Tucker method here. First step, GCF. Again, pause the video now if you want to give this one a shot, all the way, beginning to end. But I'm going to go ahead and do this one now. GCF. They all have a variable in common. In fact, not only just n, but they all have an n squared in common. I'm going to divide an n squared out of all three of them. But they have more than that. Look at the 28, look at the 16, look at the 80. You can divide all of them by 4. Four n squared is your greatest common factor. 4n squared is your greatest common factor. Divide each term by 4n squared. If you do that, you end up with 7n squared plus 4n minus 20? Is that how we get there? Yeah, I guess so. That's weird. That's how it works. Now, we're not done yet. The reason why we were done up here is because when we took out that GCF, we ended up with a linear factor. But the second we took out the GCF, we still have a quadratic. So, we continue with the Tucker method. We continue with the Tucker method with what's inside the parentheses. A times C, negative 140. Oh, what a terrible problem. No, it's not. Negative 140 may be a large number. But let's think about what we have to find. We have to find two numbers that multiply to negative 140, and at the exact same moment, they have to add up to positive 4. One of those numbers has to be positive, one of those numbers has to be negative. And the positive number should have a higher magnitude than the negative number, because they add up to a positive 4. Let's just go to our calculator. Let's just see what happens. We're trying to find two numbers that multiply to 140 and add up to a positive 4, or the difference between them is positive 4. Nope, the difference there is 68. Let's try it with the 3. Nope, I got a decimal. Not going to worry. Nope, the difference there is 31. We're getting closer. Difference there is 23. Nope. You don't have to guess and check like this. You could jump to some higher numbers if you really knew what it was. Oh, there it is. Why did I even bother using a calculator, Mr. Markey? Those numbers were so obvious at the very beginning. 10 and 14. Now remember, one of them has to be negative and one of them has to be positive. At this point, you've probably already realized that the 10 has to be negative. Negative 10, positive 14. They multiply to negative 140. They add up to positive 4. They are our magic numbers. Let's go to a T-chart. My magic numbers go on the bottom. What goes on the top? We're dealing with a 7n squared here. Sparky, what about this? Don't worry about it. Leave that for later. This is the ax squared, for the lack of a better term. It's a 7n squared. So, temporarily, I'm going to break it up 7n and 7n. Now we got to simplify. The negative stays on bottom. 7 over 10, nothing happens. 7 over 14. There we go. Let's write our terms. Vertically, 7n minus 10. 1n plus 2. Just the way you do it. You could multiply them back together. Wait a minute. I'm missing something. You could multiply them back together, but I'm missing something. Oh, that's what I missed. We took out a GCF at the beginning of the problem. That GCF, the F, stands for factor. These are our factors. This is a factor. You have to include that 4n squared at the beginning of the problem. It is one of your factors. Do not forget it. Let's try... do I want to do that one? Do I want to do that one? I want to try one more with a quadratic. I don't want to do one too crazy. Or do I? Yeah, let's do that one. I'll do it over here. There we go. One more with a basic quadratic, and then we're going to go to some higher level stuff. 5p squared minus p minus 18. Again, pause it if you want to give it a shot. Let's just see what happens. GCF, well, I got a 5, and I got a... Ooh, it's a negative 1. And then a negative 18. GCF is 1. Oh, garbage. Alright. A times C. Mr. Markey, you're going to be the death of me right here. 90. Oh, but careful. It's a negative 90. You got to find two numbers that multiply to negative 90. And, at the exact same moment, add up to negative 1. Oh, my word, Mr. Markey. Wait a minute. 90? 90. It's like 10 and 9, right? And then if I want them to add up to a -1, you just make the 10 negative. Oh, that wasn't too bad. It's almost like I'm complaining at every problem, hoping it'll go away, and then I realize how easy the problem is. Magic numbers. 5p and 5p. Don't forget it's a 5p squared. You're going to have to simplify. 5 over 10. Now that negative stays on the bottom. 5 over 9. Can't do anything. So vertically, this is now a 1p minus 2. And it's a 5p plus 9. That wasn't too bad. That wasn't too bad. You silly goose, you. I have a problem for you. I do have one more basic problem with quadratics to talk about before I move on to some higher level polynomials. One more basic quadratic problem that I want to talk about is something like this. Let's try 9x squared. Minus 16. I'll just do something basic like that. Oh no, Mr. Rocky, something's missing. No, it's not missing. The term in the middle is your b value. The bx. It's a 0x. Ultimately, when you get to the magic number step, your two magic numbers have to add up to 0. All right, let's go ahead with the Tucker method, a GCF. 9 and 16 have nothing in common. There's no variable in common. Okay, a times c. If you do a quick a times c, negative 144. Man, there's something very familiar about that number. It's a perfect square. 12 times 12. But if one of them were negative, they would add up to 0. That's it. Those are your two magic numbers. They multiply to negative 144. They add up to 0. The 0x in the middle. T-chart. What do we put in the top? It's a 9x squared. So we got to do a 9x and a 9x. And this is only temporary because we have to simplify. 9 over 12 reduces to 3 over 4. 9 over 12, keep the negative on the bottom. 9 over 12 also reduces to 3 over 4. But keep in mind now, that's a negative 4. Vertically, we get a 3x plus 4 and a 3x minus 4. Some of you watching this video may be like, oh, you could have just used like the difference of two squares formula. Yes. Yes, you could have. You could have used the difference of two squares formula. But that's not the purpose of this video. The purpose of this video is to review factoring with you. So here we go. Now this concludes the basic quadratic factoring type problems.